Hello, everybody. I hope all of you are fine and doing well. So, as I mentioned last week, today we are going to talk about the deep reinforcement learning, one of the most basic and interesting techniques that we can use for solving reinforcement learning problems. So far, what we've seen different techniques that with tabular representation, we could solve different problems, almost all of the problems that can come from reinforcement learning situation to tabular form, we see that we can solve it with, for example, Q-learning, SARSA, eSARSA, and different techniques. But the problem was when the state space is growing and we cannot break down everything into the form of tables, so that we have memory problem that if you want to code it into the form of tables, we will have memory problem. Then we saw that, we discussed that we can extend it to use the deep reinforcement learning techniques in order to combine deep learning and reinforcement learning technique together to solve problems. So today we want to see how we can do that and how we can formulate it. And we also see a nice example that already recently conducted, like in 2-3 years conducted to solve a nice problem with deep reinforcement learning. So first of all, we will talk about the deep reinforcement learning. Then today we just only specifically talk about the deep Q learning, its characteristics, and how we can use it to solve the problems. So if you want to have a general definition of deep reinforcement learning, actually what we are doing, we are combining reinforcement learning technique and deep learning technique together in order to use both of their beneficial benefits to solve our problem. So actually we say deep neural network can be directly used for function approximation, of course. Also, state as input can be directly fed to the deep network without requiring an explicit specification of the information of the environment that we have, of the features that we have. So, but the point is, in deep reinforcement learning, we try to allowing agent to make decisions instead of using the structure of deep learning purely. So that making decisions here, instead of having labels of some input data that are labeled already, we want to make decisions. So that our agent will do tries as we do in Q-learning, as we did in reinforcement learning, and state space and actions that agent can do comes as input for our network to make decisions. In simplest form, what we are going to do, we are going to implement deep reinforcement learning in order to estimate the Q values, not just directly taking the actions. So actually, we kind of, in simplest form, we can say our network is going to memorize the table so far. So we can say in deep reinforcement learning, we are learning to control agent directly from high dimensional sensory input like vision and or speech. What does it mean? It means that before this, we were considering, okay, we know the agent location. We reading the position of the agent. But now we are interested in kind of playing the games or solving the problems like human. What does it mean? It means that just with pure observation, without telling to agent that what is it in the scene, what is happening, just seeing all pure pixels, our agent realizes that, okay, this is the important thing for me. This is the, even we don't want to say where the agent is. From the vision pixely input, or pure data information, our agent tries to find out what the current state of the environment is and what can do in order to gain high reward. Of course, you may ask, is it a must to use inputs like vision and speech directly? No, it's not must. You can lower the dimensionality, do some filters, and give it to deep learning, deep reinforcement learning techniques. But the original idea that I will also present the paper, show you the idea where it is coming from, says no. Our agent tries to learn to interact with environment just purely with seeing the frames of the picture. Like a human that I'm playing game in my computer. It doesn't matter if it's 2D game or 3D game. I'm playing Counter-Strike or I'm playing simple 2D game. Doesn't matter. So my agent should learn how to interact with the environment. So we say in handcrafted feature performance that we have, it's heavily related to quality of the filters that I have. For example, if I'm not able to detect my agent position or opponent attackers, for example, if the game is 3D and you need to write an algorithm to extract those features for your reinforcement learning. For example, if I'm going to detect all of you in the class and give you some candies, if I'm agent, so detecting you can be rely on purely my vision to agent learns it, or on the other hand, I can write a filter to detect each one of you first, then give it to reinforcement learning to solve it. So of course, if I want to detect it first, then give it to that, I need another algorithm there. That can be called handcrafted feature performance that can be low still. I can have a lot of error there. But on the other hand, with using pure information, I can rely on reinforcement learning to learn everything from the state space that I have. But what is the reason that we can exploit that state space? That becomes very big, right? Too many features will come, is that we are going to mesh deep learning into reinforcement learning. So one of the most interesting thing that is useful for us is the convolutional networks. We last lesson discussed it, how it is working, and the general idea was we give pure pixely information to our convolutional layer, then it reduces dimensionality by extracting high-level features. For example, we saw that we were feeding the pure image, RGB, then it was extracting the features of like human face, arm, hand, with then lower level the angles, circles, by applying some filters. So with applying convolutional layers, actually, we are reducing the dimension by extracting important information of the picture inputs or large dimension input. So mostly I will talk about the image here, but it's not limited. It can be robot sensor, robot all joints position. It can be voice command. It can be anything. It can be LiDAR scanner input as 3D mesh cloud, and anything that can be as data can be as input here. But for better understanding and based on the original presentation of the deep Q learning, I will keep on talking on the image frames and image processing. Yeah, image-based learning of agent. So convolutional networks, we know, are important. On the other hand, multi-layer perceptrons are also important to understand because convolutional layers are in charge to reduce the dimensionality, not learning anything specific. But with combining convolutional layer and multi-layer perceptron, we saw that also we can have output of probabilities or decisions making, so that our main objective will be kind of bring the reinforcement learning into this part, kind of, to see how we can update the weights of the network that we have as function approximation in order to make decisions in order to approximate Q values and make decisions to choose actions with higher probability to act. So we have a couple of examples in OpenAI Gym and many other applications. For example, one is cardboard, that this problem can be solved with Q-learning that we already studied, can be solved with deep reinforcement learning techniques too. What we do with deep reinforcement learning, in normal solutions, we say, okay, we have the position of the card pole on the X, one dimension. Then couple of actions, we can go to the left, go to the right. And the stick should be upright. Just the action left, right, and we have the position. So the state space is not big, action space is not big, then we can use Q-learning to solve this problem. But with deep reinforcement learning, what we want to do, we want to not give the position and do not give any information directly with feature extraction. We want to purely feed the whole frame as image input to our problem. It means that your agent sees the pixel information, that these pixel information in white part are almost useless. This line is almost useless. So agent needs to extract the information that where is important part and what is happening in the scene, I'm getting reward. So this is the idea. So you can take this example, solve it with Q-learning. But we want to solve it with deep reinforcement learning. We want to today learn how to do that. We can have another example as a mountain car that is continuous here, and we want to apply some force to the car. That car can climb up to the target that we have. This is another reinforcement learning problem. We have problem like ant, or spider robot with couple of freedoms. That again, here we want to just see the observation instead of defining the actions and not the specific action, the state space with the joint position. We can say, okay, this pose is this, and for each one of pose, give input to the network, to the Q-learning or the algorithm that we have, and solve it. But instead, we want to have observation purely to see how we can deal with the problem. Or humanoid robot can be another example. Here, for example, for a humanoid robot, also we can, since we have high dimensional state space on the joints, if you consider a humanoid robot, minimum usually has 20 degrees of freedoms. Each one of joint, if you count it on the hip, rule pitch yaw, we have about 30. And if you multiply that 20 with the resolution of each joint, that can be, for example, one dynamic cell motor is 4,000 resolution per 360 degrees for rotation. And not only the joint, but also you have torque control there, but also you have the speed of the movement at each state. Then also state space is exploiting. Not only the pure image frame, there also we can consider the all state space as the joint positions as input to deep reinforcement learning to solve the problem. So this problem, if for Q-learning, is too big. But for deep reinforcement learning is solvable. Any questions so far? So what we usually do, we render the pixels to the screen as video game, and we feed it to our algorithm that we will discuss how to do that. It's kind of we render it, then we capture the frame and feed it to the algorithm. But in OpenAI Gym already in the new library, you don't need to render it. In old versions, you needed to do that, but in new libraries, you can write the RGB array, then the output automatically will be in form of array as RGB. You can use it directly to as considered as a state space. You don't need to. In old versions, you needed to render it, then capture it again. but now you don't need to do that in new versions. In examples, we will have. So if you are familiar with supervised learning, we want to say what are the differences of reinforcement learning and supervised learning, because this makes lots of confusions for students who are familiar with it or studied it. So we say deep reinforcement learning applications require large amount of hand-labeled training data that, we have some companies that they pay people or hire people. You can hire too if you have enough money. If you have your big data set, pay them money, then they label the data for you. So so on the other hand, in reinforcement learning, we need to learn it from Scholar reward that we have. So now you can maybe think, okay, can we write an algorithm to write reinforcement learning techniques to label data, to sell it? Of course you can. You should work on it to see how to train an agent that labels data. So this is interesting and make money-making idea that if you can do that, you can be rich. So in deep reinforcement learning, we calculate loss directly. If you remember, we written an equation in the deep learning part that we were discussing last week, and we calculated loss. How we did that? Directly, we calculated the loss. How much is the error based on the output that we're supposed to have? So we give input, we receive output from deep learning. Then the output, with the reference that we have, we can calculate the loss and update the gradient and update all the weights of the network. But here, then we don't have it. Why? We say a signal that is noisy and delayed between actions of the agent will propose the what we want. What does it mean? It means that my agent is like let's say path planning. My agent from here do some action. Nothing. No signal is coming, maybe. Do another action. No signal is coming. Should try a lot until go to that corner, then get a little bit of reward. Then after series of actions, we just have a little bit of feedback to update whole our network. So of course, then this is challenging, much more difficult than, okay, unless if you do something in the network, then you have the loss, then you can calculate and update the weights. Okay, clear? But of course, yeah, like if your agent, you have designed somehow the problem that you have, any action you do, you get some feedback as a reward, then you can calculate the expectation, then based on the expectation, you can update whole weights of the network that we have in deep reinforcement learning. But when you don't have it, then you don't have any feedback. In long term, you have just only feedback. That makes it more challenging for deep reinforcement learning, even in comparison to supervised learning over there. And that's why also in machine learning, we say supervised learning is far way difficult than, easier than unsupervised learning. Because in unsupervised learning, we don't have labeled data. And that's also another class of, don't mix it, unsupervised learning with reinforcement learning. Those are a little bit different. I explained it a little bit in chapter, I think, 6 or 7. So on the other hand, we say data samples usually are independent in supervised learning. It means that, like in supervised learning, we have a bunch of pictures, like let's mention YOLO algorithm. We have a bunch of frames of image that we need to detect some objects inside. Like in YOLO, for example, you need to detect, is an image processing algorithm, for who doesn't know. You need that detects different objects in picture input, like over 100 different objects at the same time, plus the location. So that's, for example, keyboard, and the location is there in the pixel. That's monitor, that's human, that's the chair. Every object can be detected with their location. Okay? But frame 1 is not related to frame 2. They can be interpreted completely independently. But what about reinforcement learning? In reinforcement learning, we say they are highly dependent because we have series of actions, which means that your agent, if goes from this direction, is totally different if I go from that direction. And the whole scenario and everything can be changed there. So we have dependency between sequences of states and dependencies, of course, based on the actions. So why we are talking about this? Do we want to make problem big, scary, and hard? Not really. We just need to know what's happening in background. But we will see if we define the structure well, all these problems will be solved automatically in background. No worry about that. But just we need to be aware that these are existing and what kind of problem we are facing. So another point is that in deep reinforcement, in deep learning, generally data is steady, while in reinforcement learning, the distribution changes as the algorithm learns new actions chosen. Again, this means that you have a data set in supervised learning, for example, image classification. You want to get image, say this is dog or cat. Data set is steady, is not changing, and everything is there. Even if its data set is very big, millions of pictures, but it is steady, no change. Again, you can get and go and take it. But here, while your agent is learning more, is doing something different, and new data is coming. And almost it is impossible to see whole state space. So that we kind of interacting with highly dynamic situation in comparison to supervised learning. Although data set is big there, but everything is there. Nothing is changing during time. Any questions so far? Okay, now let's have a look at general view of the algorithms. We say in deep reinforcement learning algorithms, we have different classes. First of all, model-free. You know what does it mean? In model-free techniques, we have value-based techniques. Now, so you know what is it? On the other hand, we have policy-based techniques. Value-based techniques are trying to, as we've seen so far, mostly trying to get the value of each state, sometimes per action, sometimes just value of state, and optimize this problem. It means that if you consider each tile as one state here, we were always defining a value for this one, value for this one, value for this one, value for this one, and we were trying to optimize it. On the other hand, we have series of techniques that directly trying to optimize the policy. We say, okay, we don't care about why we should have value. Just let's talk about the, okay, is it good to turn right or good to turn left? Those techniques are leaving the value. They don't want to consider the value. They want to consider policy directly. But it's still implicitly, kind of, they also have to, you should have some numbers to do something, right? You cannot just talking left is better or right is better. You should formulate it in numbers, but the objective there is optimizing the policy directly. So there are many techniques, over maybe 50, 100 different techniques for policy-based and value-based in deep reinforcement learning techniques that can work to deal with the problem. On the other hand, we have class of techniques that try to use both of the benefits of the policy-based approaches and value-based approaches. That those called actor critic. So actor critic says, use the benefits of value based techniques to optimize it. On the other hand, use the benefits of policy-based techniques and bring it together and name it as actor-critic techniques that we can solve the reinforcement learning problems. On the other hand, apart from model-free based techniques, that in model-free, what we were doing, we were talking that we don't have any model of the environment. On the other hand, we have model-based techniques that they can first, one series can learn the model of the environment. On the other hand, model is giving, they are trying to solve the problem. A little bit tricky to understand it, but let's say we want to develop reinforcement learning algorithm to learn the model of environment itself, not just directly solving the problem. So if you have a problem that you want to learn the model of the environment, still you can use the reinforcement learning that they are coming, this class of model based, and they want to learn the model. But on the other hand, we've seen that if you have like transition probabilities of the environment, with many algorithms, many techniques that we already seen, we can, those are coming into this class, and then you can solve the problem with those series of techniques. And of course, this can work good, but it requires good knowledge of the problem. Then you should define, for example, the probabilities or the transition probabilities that you have. If you can do that, this would be great. Any question here? Okay, so now we want to also continue with a little bit more general perspective of what's happening with deep reinforcement learning, different class of algorithms. You may hear it from your friends, you may try to study yourself, you've seen different classes of algorithms and techniques, get confused. First of all, before getting into it, I want to clarify everything for you. So in model-based algorithms, as we told, model is given, like previous slide. One of the best examples for that is AlphaZero, that we discussed at the first lesson, I guess, or second lesson, that we have AlphaZero problem that since model is given there, we can solve it with that one. On the other hand, for model-based algorithms, as we said in previous slide, we can learn the model. Also, the different class for model-free, one of the nice classes that we have is Q-learning technique. That this Q-learning can be extended to deep Q-learning that today we will focus on to study. What else we have? We have double deep Q-learning technique that is improvement in some stability of they bring you more stability. In some cases, not all the time, of deep Q-learning. We have, apart from Q-learning class, we have policy optimization techniques as a subclass of model-free. In policy optimization, we have policy gradient. That these policy optimization, what is it? It is trying to optimize policy directly, not based on the value. Just try to say, okay, left is good or right is good. So one is policy gradient. We have A to C, we have H3C, and we have PPO technique over these classes. So for policy optimization, these techniques are also famous. That nowadays, like PPO is one of the famous ones, and many researchers, if the environment is continuous, trying to use it. But the biggest benefit is not that it is really better than all other algorithms. Its structure helps us to train the models on GPU faster. The biggest benefit is that. But otherwise, you can do similar jobs with the other algorithms that we have here. Even deep Q-learning, that today I will present very nice output of this work that you will see how complex problem that can solve very nicely. Also, we have 3PO, TRPO, so another one that is also, I think, should have been between here if you wanted to say step by step which one is better. We have also one technique, deep deterministic policy gradient, that is between Q-learning and policy gradient. That is subclass of both of two, and it is also a very nice technique that is specifically used for continuous action space, that we cannot use it for discrete action space. I also solved many problems with DTPG like 5 years, 6 years ago, and that works perfectly fine. Any question here? So what we're doing now, we want to see today mostly focus on deep Q-learning as one of the basic and strong techniques. But the other ones, by looking at, you will see that the old class of Q-learning, for example, looking like each other. Not too big differences. And in the policy optimization also same. If you learn one of these, you will see that the other ones is just a little bit of changing on different steps and adding some more elements in order to solve the problem. And in addition to DDPG, we have SAC or SAC that also is also similar to DDPG and is between Q-learning and policy optimization. So we say for deep Q-learning, we can use neural network for function approximation or deep neural network. It has been proposed for playing Atari with deep reinforcement learning in 2013. That was very famous work and actually changed the path of the reinforcement learning at the time, 2013. Not very like it's almost, we can call it as new algorithm. Not too many years ago. If you want to go a little bit more in detail, as I already in value function approximation chapter a little bit explained to you what we want to do. We want to write if you want to talk about approximation of Q value, we can write Q of pi. So why I'm talking not about value function, I talk about directly Q value, because we are talking about deep Q learning. That deep Q learning tries to, per each state, estimate each action values. So keep this in your mind. We are not talking about estimating value for one state. We are talking about value per each possible action from each state. Because of that, we always will talk about the Q and Q of the pi that gets the state and action. So Q value per each state and action we want to find. We already have seen this, how to solve it with Q learning. Now we want to bring it to the estimation form, Q of the state and action, and add parameter W. And this W is the parameters that our network is trying to learn in order to find out what is the Q of the state and action. But now it is estimation, not exact value, because of course network has some error and it is called as estimation of the value that we have. Okay. How does it look like? We already, I already have shown you that we have a network here. Today we will see how state and action as input comes. We can propose state and action as input and get the Q value of a predicted Q value, state and action W. So same presentation with visual form. So instead of this value function W, we put deep neural network here. That this deep neural network can include many layers, including also convolutional layers also can be over there. But we have a problem here. What do you think is the problem in this configuration? Who can say it will get positive mark? We have a challenge here in this configuration. One minute to think. Any idea? Uh-huh. No, that's not the problem of this specific configuration. That is a challenge, but challenge for whole deep reinforcement learning. That is, of course, we can formulate it to also extract it. Of course, that's different. Any idea? So the idea is here that we can say, now if we use this configuration, we need multiple forward passes. What does it mean? It means that, so we needed to, if you remember in QLearning function, we have a max of next state. We were writing max of Q value of next action, right? So here, if we want to get the max of next action, each time we need to give the state and action as input. For same state, multiple times of, if we have like 10 actions possible there, 10 times we need to feed it here and get Q value for that one. We are at this state. Then if I can do 10 actions, I 10 times should give the input to my deep neural network and get the output of Q value. Then collect them one by one, then get the maximum, then understand which one is the max. This is the problem of this form of configuration for deep QLearning. Can it work? Of course it can work. But we have better configuration that we can say, okay, let's only give the state as input and get Q value for each independent action at the same time. So I say I'm at this state. What are the each one of the actions output for me instead? So this is wiser, and this can reduce the complexity of forward or backward pass of the actually forward pass of the my network, because when you are training, each time with calculation of the Bellman equation for updating the weights of the network that we will also dive in soon, then each time you need to, because in the deep neural network we have multiple layers, and you saw that each one we are calculating sigma and lots of mathematical things. And if you want to do each one of these independently, just for one run, we should run deep neural network 10 times more. But instead, we can reduce it dramatically over here for the number of passes that we need to apply. So let me see if you have another point here. Only the state is okay, the same. So we can say that, okay, Q values for all possible actions in a given state with only single forward pass can be then extracted. Now, we want to talk about deep QLearning that is using QLearning idea. First of all, we say, okay, let's in our network include convolutional neural network as CNN, that we call it as CNN, as convolutional neural network, that is useful to reduce the dimensionality of my problem. Is it a must to use it? No. You may decide not to use it at all, convolutional neural network. But if your state space is big, better to put some convolutional layers, proper filters to reduce dimensionality. It improves your algorithm performance. But you need to be careful. If you are proposing some technique that has pre-step calculation, pre-calculation, or filtering some data to give you deep reinforcement learning, then you should consider that if your convolutional neural network can do the same or not. Because maybe you want to use another network that that already reduces the dimensionality of your problem. On the other hand, we say agent can learn successfully control policies from raw video image data in complex deep reinforcement learning environments, so that we say not only one frame of picture, the video comes, that video, from that video we can extract frames and understand what is happening, the differences of, for example, frames, in simplest form, what's changing between two frames as our input state, and make decision what to do. Because this is also a brilliant idea that if you are looking at one image, okay, although there are information, but when you are dealing with video or series of states that are coming, the differences between two frames are more important for us, right? This can be also a considerable point to consider pixely data purely, or differences between two frames, that what is changing over there. We say a deep network can be trained with Q-learning algorithm with a stochastic gradient descent to update the weights. We studied the SGD already, for example, or different learning techniques are introduced to you. And the network that we have there for Q-learning algorithm, also SGD can be applied there to update the Ws that we have for training our network. So to solve the data correlation or dependency and non-stationary distribution of data, we have a technique called experience reply buffer mechanism. I will explain it separately very well in one slide, but generally the idea is, okay, the challenge is, I have a network and that is approximating, for example, this function for me. So this is this function that I drawn, we want to achieve it. But your network has like something like this, maybe so far in middle. Now, we say, in reinforcement learning, since the time is going on and new data coming here, like something is happening, this is continuing, and new things are happening. If you want to adjust your network based on the new data that is happening, then if you want to adjust this curve to that one, move it up, then this part maybe will be destroyed. So when you do that, you make it dark, this part will come down. And the things that happened in the past will be loosened. It's kind of like agent tries to, new things that are happening, tries to learn the new things. All this old things that already happened like 1 hour ago, 1 day ago, all getting forgotten. If you use like the new action comes, we want to update the Bellman equation, and our network should be updated based on that. So to prevent this, usually we have a technique called experience buffer, that we buffer what happened in the past, so that time to time we also train our network based on the data that already were there to adjust whole new curve to true value, true curve that we want. Any question? So in this slide, we want to see more in detail what is the reply buffer. As I explained, if you want to update the network each time but by one new state and value pair, network only learns the most recent data. And of course, we don't want to do that because the past experiences, especially deep reinforcement learning, are very important for us. And old ones will be forgotten. Solution is storing the last n experiences that we've had, and these last n experiences also is not small, maybe 10,000, 100,000 times of trying of agent in different situations. That usually we store them as tuples in the in programming form. And in the memory, we can write, okay, state, action, reward, and next state, next action that happened. We say What was the state? What was the action that you did? And what you get as reward? And what was the consequenting state and action that are there for you? Because in some scenarios, these are also dynamic, and you don't know what are them. Because, like for example, in image frame input, after doing the state action reward, you don't have model of environment. You don't know what's going to happen, what new state is, and what will be possible actions over there. Because of that, we usually also keep them as memory for our agent. And on the other hand, aim is to uniformly and randomly sample previous transitions, and the smoothness of training will be the training procedure will be more smooth based on the past behaviors that we've done. So if we randomly draw from the pool that we stored there, we can call it as mini batches, training with mini batches, which means that we have big reply buffer, and the experiences that we have, we can randomly choose as small mini batches, like 50 of them, 128 of them, some mini batches, and train our network by that batch training, so that instead of letting train to try to adapt the network by new data, we will try to say, okay, if the action that I'm doing now is good, like 10 times, 100 times before the action that I've done, how it was, and train my neural network, deep learning. Any question? So we have now two concepts here, reply buffer and the mini batch update of the neural network. We have a couple of challenges here. Let's first indicate the challenge and then answer it. We say using histories of arbitrary lengths as input in neural network is very difficult, first of all. For example, if we talk about the episodes and we consider input as episode, it means that my agent start from here, move, one time, finish. After 100 steps, one time, finish after 20 steps. Then your input for neural network is not fixed size, that you cannot do that. So that's one challenge, that you should define somehow the situation, the problem that you have to be stationary. That we say to solve this Q function only works with fixed lengths. Then we try to limit the size, kind of that history should be in fixed size. Other challenges, update of the one network can be very unstable. Why? Because or better code with slides. I think in next slide I have it. I don't need to draw it. So in supervised learning, we said we have data and labels to calculate the loss. But here we don't have label. And all the calculations, all the Q values should come from one neural network. All the Qs are coming from one neural network. It means that the update and calculation, before improving it, again, I need to ask him, what was the previous Q? It's like your memory is not able to, you're not able to memorize a number at the first time that you're reading. You should practice it multiple times. But the loss that you are calculating is also based on previous one that has error. So improving something with error is difficult. That we say updating one network in basic Q learning is difficult and challenging. But although it is working, it's presented by original paper. I will discuss it today for you. And I will show you another example that it can improve it by adding one more network that we will see how now. We will see how soon in next slides. So the solution is, first I've written the reason. The reason is if we have changed the target each time, the model updates itself and it creates instability. So that we will discuss it in next slide soon. Okay, so keep that in your mind. We will discuss it soon. We say deep learning objectives can be include creating a single neural network agent or choose two of them here that is able to successfully learn to play many of the games as possible, not without changing the whole structure of network. And no game-specific information or hand-designed visual information we want to give to the deep learning. It means that we want to one-time build a structure for our reinforcement learning that is able to play many games with the same thing, with same parameters, with same hyperparameters. Just visual input comes, and the actions will be the output based on the reward. And learning only by video, reward, terminal signals, and the possible actions. Like what human does. So the information like position and environment, only agent observes from image. We discussed it multiple times. Clear should be for now. We want to receiving reward that represents the game score. So we have already the game, like all the games that you have in your cell phone, for example. You play it, and finally the game says, okay, what is the score? You are winner, you are loser, you get mark, or you lost the game. The feedback about the actions may be only received after very long time. So you may play a game for 30 minutes, 15 minutes, then you are winner or loser. You don't get any feedback from in the middle, for example. You lost for example, your health in the game. An observation of current situation, only the current screen, and since sometimes it is not possible, we should figure out how to deal with it. What does it mean? It means that sometimes you see the game, but all the things that are happening are not over there. Maybe the enemy is in backside of something and they're coming. And it was like crossing some object. Like, let me show you my phone. So this one is crossing from here, coming toward me. But at this time, it's hidden suddenly comes out from here. So we say that, okay, it's not always possible to see all current state from the environment. And because of that, also there are some approaches to consider that. We say sequences of actions and observation is important, and we should kind of design our solution that if the problem is sequences of the distinct states are considered. What does it mean? It means that you can consider, for example, 10 frames or 2 frames or 3 frames as state space to give to the environment, to the problem that you have. Not only one frame of picture. You can give like 3. You can give like 5. That shows you sequences of what is happening. Although the state space is growing, but the benefit is that we have deep reinforcement learning, and deep reinforcement learning allows us to make it bigger as much as we want. So that's okay. Then we can apply convolutional layers, decrease the dimensionality, and provide it. But then we consider the sequence of actions as input. That for the states that we don't see. Okay, for this one, we will see soon in next slides. So a challenging reinforcement learning testbed that presents agent with high-dimensional visual input to play Atari game is like, we can, for example, propose a RGB pixel frame, like 2010 times 160 frame, at 60 hertz of the input frame. Then then the output will be diverse as the tasks that we want to do, and some of the tasks are also difficult for video game playing for us, for solving deep learning. To deal with this problem, playing Atari, we have very well-known paper, first publication that successfully solved this problem. The title is Playing Atari with Deep Reinforcement Learning. You see it's proposed in 2013, and number of citations is 10,300. That it means that 10,300 different research have been conducted that refer to this paper, and they try to develop this original work. And this is what kind of revolution happened in solving different problems with combining reinforcement learning with deep learning. So I'm also recommending you go to study that paper to see what is happening there. So the points that we discussed are clear for you so far. Any question? Okay. Now we want to say, let's mathematically talk about value function approximation and how we can bring it into the deep reinforcement learning, specifically deep Q learning. In last chapter, 2 chapters before, we talked about the general value function approximation and how Q learning equation can come inside. We have the same equation, just have a look. We can define objective function as E of W, also known as J as W, to minimize the loss between target value and prediction value. So what does it mean, target value and prediction value? Have a look here. We have the error, E of the W, that this W is the weights that we want to find for our network. Our network that is equal to expected policy, that is differences between the value pi of S and predicted value of the S and W. That what we call them, we said this is target value that we want to reach, and this is the predicted value that comes from our model of the environment. Keep this in your mind, that predicted value S and W's originally in value function approximation is the value that our approximator is trying to give us, and this is the value, real value of the state that we have. But actually, we don't have that too now. The fact is that also we don't have it. If we have it, then we don't need this one, actually. But now we want to see how to kind of figure it out if we don't have it also, but we want to calculate the error between these two, how we can bring it to the game. So how we can do that? So I have a point here. We say this is an optimization problem that can be, we want to find the parameters W to minimize this error. For example, mean square error of the problem. So not only we don't have it, but also we want to minimize the error by finding best parameters for W that is representing my network weights. Clear? Any question? So for updating the weights, it's clear. For updating the weights, we can use SGD, stochastic gradient descent. In deep learning section, we studied how that is working. That's we say, okay, it's already solved. If we have the values and differences, we can update the weights with SGD. But let's see how we can take care of that part. First of all, we have a standard assumption that feature value rewards are discounted, same as what we've done in Q-learning. Second, the network can be trained by minimizing sequence of the loss functions of E of i's of thetas calculated by change at each iteration. That it means that now I can write at each time step, the error, instead of W's, I'm putting theta here, theta of i's, that at each time step, the error can come from expected yi and the q of the st, at, and ti. So this is prediction as previous here, this part. Instead of value, that was for value. Since I am working with deep Q learning, I put Q here, then I have a state action and the weights of the network. But what is this y over there? The y over there is target value, that this target value can be calculated by the equation that already I've seen. Instead of y, I per each step, I put the reward of the state and action that I have, added by discounted, maximum of the next actions, next values per actions that I have. So, but the point is, again, these values are coming from same network. I extended this part for value calculation to Q value calculation first. But already I told you we don't have it. We don't have the we don't have this part. But although we don't have it, we rely on the network that we have. Whatever it is, we predict it, get the maximum action, then discounted it, then added by reward, then we have it as yi as output. Then the differences of yi to the power of 2 are MSE. We want to optimize my network weights per each iteration that I have. Questions? I mentioned the point. I said if you have one network, we have a little bit challenge. And I said later I will explain it. That's what's reason here. That since this part and this part, that is this part, both are coming from one network, usually the output is unstable. Not very reliable. And this has a solution. That also I will show you how we can improve the stability over here. So that I can say instead of having one network, I can have two networks. One for this guy, one for this guy. But one of these will be updated too fast every time. One of them I want to keep it and update it sometimes. But they are copy of each other. So just I think it was a little bit more clear to mention it here. So what happened? What we changed based on the Q learning that we already knew? Everything is same almost. The reward discounted maximum of this one, and we want to optimize the weights by finding the differences of those. But this time instead we put deep reinforcement learning, deep network here. The output comes from deep network. The output of each one of these next state actions come from deep network. And what is the output? Just Q values, same thing. You can imagine instead of this one, we have table again, and from table we extract them. It's the same. The values could be lookup table, go to the table, what was the values. Instead of those, deep network says, okay, what is give me as input state action and the weights that I have already, then I give you value. Then you replace it, then find the output as error, and based on that error, use stochastic gradient descent to update the weights of same network to improve it. Okay? We say the parameters from previous iteration, theta minus 1, are held fixed when optimization of the loss function, ei theta, should be used is one way. Second way, that as I mentioned, we can use, instead of keeping fixed that one, we can use two independent networks. Fixed just only for calculation, then later, of course, we need to update it. Just for the calculation, we keep it fixed. Now, how we can calculate the target and predicted values and bring the value function as Q-learning? We can say we already seen it. We can talk about differentiation of the loss function with respect to the weights, and the following loss can be calculated. So this is same thing. Just I put it instead of y, the same equation that we've seen in previous chapter. Expected reward added by discounted maximum of the next action subtracted by what? The current state action. That this is come from network one time, and this one again come from network one time, getting max and calculating. Then we have E of the W. And based on that, what we can do, we can calculate the gradient and update the weights of the network that I have. And we said that everything is same. We add the learning rate. What is the learning rate of learning our weights on the network? This can be like how fast I want to update the weights on the for my network, and the same equation exactly here. Just we add one more element as gradient or slope of the how fast data is changing, so that it can improve and help us to update the weights over there. This is already has been given. We don't need to change it for deep Q-learning, and basically in most of the versions that we have, we just implement and develop it and engage it with the problem that we have. I restated one important point. The real target value, this one, in practice also prediction from model, that while in supervised learning we didn't have it. So the point that I already mentioned multiple times, but I jotted down there for you so that when you're studying later, you can make sure that you don't miss it and don't confuse it. So we say the network weights are updated after every time step, and the expectation are reduced by replaced by another single samples from the behavior distribution from the experiences. We explained already. Now you know what does it mean to optimize the loss function instead of computing full expectation. In the previous gradient that we have, that is computationally expensive. As I mentioned, we can use SGD. We don't use gradient descent. We can use SGD to calculate the loss function. That is some complementary points for deep training one. Now let's a little bit have a look. What is the target network? I said, okay, we can split it into two. So we say, in fact, we can create a same network, whatever network we're defining. We can create another copy and another sample, another exactly same detailed network, and we call one as target value and another one as predicted value networks that we can deal with the instability problem of the learning convergence. So that target value was this part. And predicted value was this part. So this was prediction network, and target value, we wanted to achieve this part over here. So we can use two networks instead, target network, prediction network for each one, target and prediction. And how it looks like this. We say we have the same input, state space as input. Instead of using one network in the center, we can copy the network into two parts. One is prediction network, another is target network. Prediction network is in charge of giving us this value, the prediction value, this part. And target network is in charge of giving us the maximum of next states. And what What's happening? We are separating them, and when we want to calculate this, we ask this part from this network, and we ask this part from this network, simply. But the point is, the prediction network will be updated always. But target network will be updated at some iterations. Like we update like every iteration. This one after 100 or 1000 or 500 times, something usually between like 50, 100 to 500 is common. After 500 or 400 steps, exactly we copy all the values, all the weights, whatever is happening to target network. Nothing special. In creation part, we create two, we start training. This equation answer comes from here. This equation answer comes from here as output of those networks. And every, for example, 200 times, 400 times, we copy whatever is it here. Again, we continue improve it. Copy here, we continue improve it. And based on that, we calculate the weights of network, update it, and copy it here, and we continue this to train our agent. How our agent is getting trained by this reward that gets from states as input and the prediction output from Q values that I have, which action is best, and getting the max and updating this calculation. The same calculation that we've seen in Q-learning, the tables, the values that we saw example. Exactly, if we put it here, is same. Just here comes from networks, that's it. And then we calculate the, update the loss. Instead of updating value on table, we were removing the value on the table and putting there. Here we train the network instead that can answer us when we asking. Clear? Like instead of this whiteboard that I can write some data here, I ask one of you guys, my network stay here, whatever I'm saying to you, remember it. And you should answer me, whatever I'm saying, instead of jotting down here. Then I see that that guy is like unstable and is not remembering when. I ask another guy, stay there, and after some iterations, I pass the copy, the information to other guy and get the differences and update this guy. So the looks like this if you want to imagine what's happening as each one of these as brains. Clear? So one of the notes points that we should consider in practical implementation that usually we don't see in theory, but I usually try to teach in somehow that you practically can bring it to the code and bring it to real environment, not just only memorize everything. We say reducing the input dimensionality is well known, whatever the problem as you have. Although we said that we have deep network, although we said that, okay, you can feed all pixely information input, but still you can throw out some information that you know they are useless. Then if you can do that, do that. Like one of the common things that I will show you also if you have time in the code. So you have an environment, for example, card flow, that the agent is here, right? Here. Then the working space like here. Then you know that all the time the agent will be around here. Why you should have these parts? So you can cut it, throw it out. So based on problem that you have, you see that you have lots of useless information, cut it, throw it out. That's one thing that we should consider. Or you say, this is very important. So this image is RGB. And in OpenAI Gym, when you capture as RGB array, then it gives you RGB frame. But do you need color here? Of course you don't need. This is control problem that you should balance this one. Color is useless. Then throw it out. Instead of having this RGB, bring it to grayscale. To reduce your state space 3 times more, then you focus on the problem. You don't need color information here. So on the other hand, you can use convolutional neural network to downsample it. For example, you don't care if what is this pixel, 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 pixel in this specific problem. You care where it is, and you can apply convolutional neural network, reduce dimension, like just put a mark there, or all these can be as a pixel. Like put lots of convolution that gives you something like unreadable, like something like this, but gives you the meaning. Where is the code? A little bit of information should be extracted, or maybe the corners, just 2-3 corners will be extracted. Then that is your input. Then here and here will be extracted. If you add lots of convolutions, then it will be something like sketch. Because this is like 2D I'm drawing. We have part fall in 3D. You don't care if it's 3D, 4D, whatever it is. It's fancy, beautiful. We just care about control. Then you reduce the dimensionality. So as I mentioned, we don't need most of the time details of the problem. For example, like I have an industrial arm. I want to develop deep reinforcement learning algorithm to grasp it. So do you care if it's fancy or beautiful object or whatever it is? No, just the edges are important, how to grasp it. So because of that, then you don't need details. Also, it is very common to downsample the pixels. Like if the frame is like 210 times 160 pixel, you don't need that too. You can downsample to reduce the resolution as much as you can. Not all of those also reduce the resolution of the video frame, depending on the problem that you have. And as I mentioned, capture the playing important part area. Just cut it. If you are certain that this is the important area that I'm going to work, then you can cut that area. Now we want to see the procedure of the algorithm, put everything together. So keep this in your mind that we had this equation, Bellman equation for updating the gradients. Let's have a look how the algorithm flowchart is, algorithm procedure is working. So we have, first of all, let me mention, we have different also variants, different versions. This is the original version. Maybe some try to improve it, some try to change it. In different resources, you will see some differences, but all idea is the same. And also today, I will show one improved version of these that uses 2 networks as target and prediction that I explained to you. That improves this one a little bit. So what we do, initialize reply memory D to capacity N. We say we want to have initial memory. And keep this in your mind. You have memory, and you are sampling batches from this memory to train network, but before filling this, we try to avoid to sampling inside. So don't sample from input in the beginning. We usually start from some certain time of trying, then start to sampling and training network. This is also one point. Try agent a little bit, train, try, then you have at least like a number of items inside and sample inside. That also some of you in development step forget to do that. These are implementation notes. So initialize reply memory, then initialize action value function queue with random weights. Then for episode 1 to m, for each one of the episodes, we initialize the sequences of the states that, and we pre-process the sequences as one like kind of a set that is including the states. Then for each time step, with probability of the epsilon, select a random action with epsilon greedy. Otherwise, select maximum of the Q. That this is coming, the maximum of the next action comes from the network this time, not table. The output of the network, gives us the action based on this theta that we have, the parameters. They get the maximum and run it. So if you look, is exactly the same as Q-learning with epsilon greedy, random with some probability or get the maximum. After that, execute the action in the emulator or real environment or whatever it is, and observe the reward and get the new state. Because if your agent is doing action, we move to the next state and we get some reward or we don't get it, whatever. Then after that, the state, next state will be the current state, and we can then store the transition, create a transition for the memory that I said, like we have different elements. Here you can see that state. That this state also can be set of states, not only one state. Can be like 2 frames, 5 frames, 10 frames, depending on what we are doing. Set of states, action, reward, set of next actions per with this one. After that, what we do, sample mini batches from that memory. So set of, depending on the size of mini batches that we define, how many we want to take and train network from D, we take them. Then what we do, we calculate the yi, that we said the yi is this part, the yi by the equation, that is if the state is terminal, because we don't have next state in terminal, so when it is finished, we don't have next action, right? Then just reward comes. But if it's not terminal, what we did also in Q-learning, if you look at the code, reward added by discounted max of next actions, 2 conditions. Always you run this in the code. When it is terminal, then just run reward. Then what we do, perform gradient descent step on yi that we calculated here, subtracted by q of this one. That this q is over there, and this one is over here. That with value function approximation, we've seen this exact same equation in a couple of slides ago. And gradient descent or statistic gradient descent then updates this term over here for my weights. And we do it in for loop for all episode. Every time update the network. One network. We have here only one network. Then train it based on the reward. So did it work? Yeah, of course it worked. This is the paper, and this algorithm did great job. So let me see if we have. Yeah, here I'm going to explain the paper a little bit, what is happening and what they've done first. So I think we can have 2 minutes break, then continue. Any questions so far? Okay, just 2-3 minutes break, then we continue. First, I explain the model-based and model-free, then we continue with the paper and example. All right. So now let's continue with, first of all, answering that Q-learning, deep Q-learning is model-free. Why model-free? Same as previous techniques that we talked about. It is directly using the samples from the environment without explicitly constructing the environment estimation that we have the transition probabilities. So since we don't propose it, since we don't know it, we can say that deep Q-learning is model-free, like similar to Q-learning. On the other hand, it is off policy. Why it is on policy? Because if you consider this max part over here that we were doing in the Q-learning also can cause different actions to be chosen by the epsilon greedy action selection that we've had. So that the update of the Q value on the network, similar to Q table, since it can be different with the action that really robot is choosing to do or agent is choosing to do, then we have off policy technique for deep Q learning too. So now you may say, if we apply instead of deep Q learning, deep SARSA learning, then what will happen? Then of course we will have on policy instead of off policy, because in that case the update of network will be steady with the action selection over there. So same concept, we have it here. Again, I'm just mentioning the maximum of these can be different with the strategy of the epsilon greedy that chooses the action, because the update of the network with the value that we are doing can be different from whatever we're running in the environment because of epsilon greedy that can be random in some cases, then it is off policy. Okay? And if you remember, on policy and off policy and all the techniques were just referring to update of the Q table there, but here the network, the training network. So we say deep Q learning for Atari games by original presentation of paper have been used 84 times 84 times 4 image that produced by this set. So the input is state space considered as this size. Then first hidden layer applied by convolutional layer of the 16 of the 8 times 8 filters. So, so the filters that we've studied, and they define the stride of 4 with the input image and the applying ReLU as the activation function. Okay. Then second hidden layer, they define the 32 of the 4 times 4 filters with stride of 2, and they again applied the ReLU on the second layer. And the final hidden layer is fully connected and consists of 256 units. You see, very simple deep learning structure for the training of the network. And after that, the final output layer is fully connected layer that is a single output for each valid action that represents which valid action should be, like what is the value for each valid action that should be chosen by that state. So the number of valid actions varied between 14 to 18 depending on the game that they applied, because as I told you, the motivation, the idea was to applying one network on different games without changing anything. The same scenario comes, the same states, the same input frame comes, the same size comes, the output will be proposed, but since the games are different and the actions space is different, the only differences is number of the actions as output, 4 to 18. They consider all positive rewards only, and to be considered as 1. And on the other hand, all negative rewards only as -1, and leaving 0 rewards unchanged. So depending on the game scenario, they kind of normalize whatever is happening as -1, +1, and 0. Instead of one game, it suddenly gives reward of 100 or something, it scores. Like you kick the ball, it's scoring 100. So all the games are flattened to 1, -1, and 0 to get as reward. They train 10 million frames. Why I state here? Because sometimes I see the students are trying to train algorithm and they don't know how much should be, how many training is good. Is it high? Is it small? If you see many samples, then you can almost realize how many training episodes, how many training iterations you should let it. For this size of problems, for example, 10 million frames has been used as training, and they put it 1 million only in the reply memory. So 1/10 of the learning has been stored in the reply memory. So when you are asking what should I define as size of reply memory, you can have look at different examples that successfully solve the problem. So they used a simple frame skipping technique that helps to drop the frames that are useless. What does it mean? It means that they've considered, okay, if you have frame A, B, C, D up to 30, then should we feed all of them to the network? The answer is not really, because they are repetitive. Like maybe 5 frames, even agent couldn't have time to move to the left or right. So they drop those. They only keep the chains and use the frame skipping technique. That agent sees and selects actions every case frame instead of every frame, and the last action is repeated on skipped frame like 4. What kind of games they've solved at the initial state, you can see here. They've solved beam rider problem. They've solved breakout problem, punk game, sequests, and space invaders. So all these problems with deep Q learning has been solved just only feeding the pixely information as input. This game. Of course, they have different kinds of actions, and based on the actions, deep Q learning has been learned how to play the games. What was the result? Let's have a look at the result of the games. You can see different games over here on the table that there are different algorithms has been applied on it. For example, SARSA. For example, most importantly, human here. They let a human play the game, and the deep Q learning that is proposed, and I explained the structure for you. So you can see on the results here that deep Q learning, for example, on most of the games even beat the human. Like here, 168 is the result, but for human is only 31. Much better than human. In this game also 470 over 367. In Punk, human got -3, but the deep Q learning got 20. In another game, so human was better here, and here human was better. On the invader, human was better, and here human was better. In 3 of games, the simplest deep Q learning has been able to beat the human, but the other ones are also not too bad. In comparison to SARSA, of course, far way better. You can see the results far way better. 5.2 only is 168, and mostly beaten all other techniques and algorithms. So what else we have? As I mentioned, we had the problem of the instability based on the target and prediction network update. But there are many different approaches that has been proposed to improve it. And one of the ones that is very interested in, and one of our students found it out recently, the paper, and it has been solved, very complex problem of control with only using deep Q learning with double network for copy of double network for target and prediction. You can see the agent in 3D environment that learns how to walk, learns how to control and balance on when he's walking, if there is like some obstacle, hits the obstacle and how it can recover. You can see the result over there, that what is happening on the hitting to the obstacle. You can see how it's trying to learn different complex games and sports, skating. In different scenarios, like they give more freedom for the controlling and using the hand, adding more motions to control the skateboard. You can see walking on and controlling, balancing on the ball. Same network, all of them are with same network. And bigger ball, much more funny. Walking in different directions with push recovery. And continuous push of the agent. And balance control to try to not move even. And if you look at it, it's like kind of learn how to do it really like human. And doing much more complex actions, but something funny will happen here that, yeah, the agent can do stupid actions in the environment. And how to learn how to stand up and do much more complex actions. So by looking at this is for me even was interesting application and interesting work, because it was using the most basic deep Q learning algorithm, just only with adding two networks and creating control fragments on physics-based characters, so that it's not feeding whole image as input, but instead creates control fragments as input. Status space is smaller, action space is smaller, but the control result is very nice, even though with using the most basic concept of deep reinforcement learning that today we will study together. You can study the paper itself. I highly recommend to you go have a look, read it in details, and also you can watch the video and the more explanation in detail. But I'm going to, and here you saw that the bungle board balancing too. But I want to just show you the general architecture of the implementation, that it is, you can see that user control commands as it states are coming to the queue network, the same queue network that today we studied, reward function that defined for this specific problem depending on the task that they have. They have simulator and the actions, that all these coming from tracking controller and control fragments. That these control fragments are predefined by controller, that reduces the kind of trajectories for the actions that can be chosen for each series of state that there is. Then action will be selected, then the queue network will be updated. That's like not very extraordinary thing, just putting all elements all together and simulating it. And of course, if we can solve it for simulation, the humanoid robots, the robots that we have also can learn the same idea and just put it and let it robot to train the same thing. So their motivation was like using finite action set, consists of control fragments, and they extracted from a perceptual tracking controller by simulating and learning. On the other hand, let's have a look at the network that they have. Very simple, even they don't have convolutional layers for that. They have the states of the environment based on the robot, they're based on the agent reading like the status of the position, and the U is the whatever the task that they wanted to do. For example, you want to walk, control on bungle board, or do something else. The same network they have used for different tasks, and the task as input. You see fully connected network with ReLU as activation function, first layer, second layer over here, and finally the output is same Q values that we discussed. The Q values comes and you can see which one is like bigger action. Then they, for example, choose the maximum action for Q value for each action. Then I stated the whole algorithm that they proposed here, and I indicated the differences. What are the differences with what we studied with the general and original paper for deep Q learning? You can see that a little bit change in the probability of the selecting random action over here, and most importantly, they have the update of theta with batch of a stochastic gradient descent, that they are doing the backup of theta to theta predict theta. It means that they have two networks that they are copy, and every nth time in nth step they back up in this network to another network, and they split it network into two to make it more stable to train. Nothing very specific. When you train, you just I will show you in the code also. Just you need to define two networks, then just sometimes copy it to other one. Then sometimes ask this one, and sometimes ask that one. Prediction for every iteration, target for every nth iteration. As I told you, usually 100 to 400 iterations we define. Any question? So that's very nice that you have some of you define your. I know that your project is based on deep one. If you are interested in, you can do the same one with something similar program here. So what are the advantages of bringing value function approximation into game by deep learning? Was that we are solving memory problem basically as first stage, and secondly we are generalizing the problem that we saw that really we have a network that can play different games with the same network. Just training same network, we can play different games. So these are the big advantages of the using value function approximation. Most importantly, deep reinforcement learning.